Three potential energy functions and they look nothing alike. mgy for an object near the Earth's surface, 1/2 ks squared for a spring, minus big G m1 m2 over r for two gravitating masses. One identical recipe produces all three, and each formula is only fixed after a choice physics cannot make for you, where to put the zero. We've already met all three of these forces: gravity near the Earth, the spring force, universal gravitation, as external forces acting on a system. The external work equaled the change in the system's kinetic energy, and no potential energy appeared. Now redraw the boundary and bring each force inside the system. For an internal conservative force, the definition from last video takes over. The change in the system's potential energy, delta U, equals minus the work done by the conservative force, minus the integral of f dot drr from the initial state to the final state. Same three forces, new bookkeeping. Every derivation ahead runs one 5-step recipe. Step 1. Write the internal conservative force. Step 2. Write the displacement dr and take the scalar product. Step 3. Integrate from the initial state to the final state. That is the work. Step 4. Negate it. The change in potential energy is minus the work. Step 5. Choose a convenient zero reference, turning delta U into a potential energy function U. The recipe never changes, only the force does. Why is step 5 legitimate? Delta U is built as a difference. Introduce a function U with delta U equal to U sub f minus U sub I. The physics determines only that difference. Add the same constant to U everywhere and it cancels from every difference, so no measurement can detect it. The zero of potential energy is therefore not a fact of nature. It is a bookkeeping choice, free for us to place wherever the algebra comes out cleanest. Each of our three systems has one obviously convenient place. First run, gravity near the Earth's surface. Choose the system to be the Earth and the falling object together. Gravity is now internal. Each state is specified by the object's separation from the Earth's center of mass, together with their velocities. Put the origin on the Earth's surface, positive y pointing away from the Earth's center. The Earth's own displacement is negligible, so tracking the object alone is enough. It starts at height y sub I and ends at height y sub f. Step 1. The force. Gravity on the object is minus mg in the j-hat direction, constant straight down. Step 2. The displacement is dy times j-hat, and j-hat dotted with j-hat is 1, so f dot dr collapses to minus mg dy. Step 3. Integrate. The work from y sub I to y sub f is the integral of minus mg dy and with mg constant. That is minus mg times the quantity y sub f minus y sub I. Step 4. Negate. The change in potential energy is mg times the quantity y sub f minus y sub I, mg delta y. Raise the object and the system gains potential energy. And the energy belongs to the Earth's object configuration, not to the object alone. Step 5 for gravity. Put a 0 at the surface. Let the final height be an arbitrary y, the initial height 0, and declare u of 0 equals 0. Then delta U equals U of y minus U of 0, simply U of y. Steps 1 through 4 gave delta U equals mg times the quantity y minus 0. Equate the two, U of y equals mgy with U of 0 equal to 0. Height above the surface now directly measures the system's stored energy. Second run, a block of mass m on a frictionless surface tied by a spring to a wall. Put the origin at the block's center when the spring is relaxed, and point positive I hat, the way the block moves when the spring stretches. The wall does exert an external force, but its contact point with the spring never moves, so it does no work. Only the spring force, internal and conservative, does work here. Step 1. The spring force is minus kx in the I hat direction. Not constant now, it grows with the stretch. Step 2, the displacement is dx times I hat, so the scalar product is minus kx dx. Step 3, integrate from x sub I to x sub f. The work is the integral of minus kx dx, which evaluates to minus 1/2 k times the quantity x sub f squared minus x sub I squared. Step 4, negate. The change in potential energy is 1/2 k times the quantity x sub f squared minus x sub I squared. One elementary integral. The recipe supplied everything else. Step 5, the springs 0. One configuration is obviously special. The relaxed spring at x equals 0. Start at equilibrium, n at an arbitrary x. The recipe gives delta u equals 1/2 kx squared, and a delta u also equals u of x minus u of 0. Define u of 0 as identically 0, and the function follows. U of s equals 1/2 kx squared. The square makes it symmetric. Stretch or compress the same distance, store the same energy. Third run, two objects, masses m1 and m2. Draw their position vectors from a common origin. The center-to-center separation is r21, and along the line joining them sits the same unit vector from last video, r hat 21, pointing from mass 2 toward mass 1. The gravitational attraction acts along that same line, falling off as the inverse square of the separation. Force and the displacement share that line, so this is really a one-dimensional problem in the separation R. Step 1, the force on object 1 minus big Gm1m2 over r squared times r hat, the minus sign encodes attraction. Step 2, the displacement is dr times r hat, so the scalar product is minus big Gm1m2 over r squared dr. Step 3, integrate from r sub I to r sub f. The antiderivative of minus 1 over r squared is plus 1 over r, so the work is big Gm1 m2 times the quantity 1 over r sub f minus 1 over r sub I. Step 4, negate. Delta U is the same thing with both signs flipped. Pull the masses apart and delta U is positive. Separating attracting objects stores energy. Step 5, no surface here, no equilibrium, but the formula singles out one separation, infinity. Delta U has two terms and the big Gm1m2 over r sub I vanishes as the initial separation grows without bound. So set r sub I at infinity with u of infinity identically 0. What remains is u of r equals minus big Gm1m2 over r. At every finite separation, the potential energy is negative, climbing towards 0 as the masses move apart. The deeper the value, the more energy it takes to drag the objects out to infinity. Now put the three runs side by side, the same 5 steps in every column, a different force in, a different function out. Constant force in, linear function out, mgy. Force linear in the stretch, quadratic function out, 1/2 kx squared. Inverse square force in, inverse first power out, minus big Gm1m2 over r. The formulas look unrelated, the derivations are identical. Three curves carry the whole story. The line mgy crosses 0 at the surface. The parabola 1/2 kx squared touches 0 at equilibrium. The curve minus big Gm1 m2 over r reaches 0 only at infinite separation. Physics fixes each curve's shape. Its vertical placement is yours because only differences in potential energy ever enter a prediction. Slide any curve up or down and every difference survives. So pick the reference that deletes a term or marks a natural configuration, say so clearly, and the function is pinned down. Path independence is what let us define a potential energy at all. The third law told us it belongs to the pair, not the object. And this recipe turns any conservative force into a function of configuration. One recipe, 3 potential energies, and the 0 is always yours to place. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.